When you look at your phone, have you ever wondered about this? The phone's light. How does it reach your eyes? In earlier understanding, we assumed light travels in straight lines. Simple and clear. But light's actual journey is far more complex. Since ancient Greece, philosophers sought to explain light's nature. But true insight into light came with quantum physics. In quantum physics, light behaves as both wave and particle. First, let's explore waves. Light's wave nature was proven by the double-slit experiment. When light passes through slits, due to interference, it forms on a screen a pattern of bright and dark bands. This is an interference pattern. The spacing and brightness of these bands reflect the nature of interference. You'll notice the bands are evenly spaced. Farther from the center, the bands fade. This shows light doesn't always travel straight. When meeting obstacles, it bends and spreads. That's its wave nature. Light's wave behavior also appears in color. Different wavelengths produce different colors, from ultraviolet to infrared. Visible light is a tiny part of the electromagnetic spectrum, yet it shapes the world we see. Shorter wavelengths are blue and violet. Longer wavelengths are red, like in a rainbow. White light refracts through raindrops, with wavelengths bending at different angles. This creates the 7 colors of a rainbow. Refraction highlights light's wave nature. When light moves between mediums, its speed changes, causing it to bend, like a straight stick in water, appearing bent. For the particle model, in 1905, Einstein proposed the photoelectric effect, a classic proof of light's particle nature. Light hitting a metal surface ejects electrons. The key is, brighter light doesn't make electrons eject easier. The light's frequency must exceed a threshold. Only then it works. This phenomenon can't be explained by waves. Waves are continuous. But if light is discrete particles, photons, each carrying fixed energy, its energy tied to frequency. It makes sense. Einstein's explanation was brilliant. Photons are tiny energy packets. These packets hit the metal, and if their energy suffices, electrons are ejected. If not, nothing happens. Electrons stay put. How do we prove photons exist? The Compton scattering experiment. X-ray photons collide with electrons. Their wavelength lengthens because they lose energy to electrons. This can't be explained by waves. But the photon model fits perfectly. In 1926, Schrödinger introduced the famous Schrödinger equation, a cornerstone of quantum mechanics. It doesn't directly address light, but describes wave functions of tiny particles evolving over time. The wave function, an abstract concept in quantum mechanics, gives the probability of particle locations. It describes particle distributions. Each particle has its own wave function, including photons. Light's quantum, while Schrödinger's equation mainly describes electrons, photons, as quantum particles. Follow quantum mechanics too. Photon behavior is described in quantum terms. Photons have their own wave functions. Despite having no mass, they still show wave-particle duality. In truth, light doesn't choose to be wave or particle. It depends on how we observe. Observation shapes its behavior. In some experiments, light acts as a wave, showing interference and diffraction. In others, it behaves as particles, like in the photoelectric effect or Compton scattering. Light's wave-particle duality enables many applications. In quantum computing, photons serve as qubit carriers. Their superposition states give quantum computers unmatched power. over classical computing, quantum communication and lasers. Also rely on light's unique properties. Do you know other ways? This property is used in daily life.